Very good morning, students.
Good
Good
morning, sir.
morning, sir.
Let us start with the discussion without wasting any time. The last class we have been discussing about inductive effect and different examples in that perspective, and also start with resonance. And this is how the resonating structure in benzene can be. So you can have these two structures where the positions of pi bonds they have been changed, and we'll be having a resonance hybrid like this where the pi electron density is under complete delocalization. So let us start with resonance and what are the conditions for resonance. If you look at the condition for resonance, students, there should be conjugation or not. If there is no conjugation, there is no possibility for resonating structure. System must have conjugation. That means parallel p orbitals with at least one electron pair. With at least one pi electron pair should be there. So how many types of conjugation systems we have? Let us list them out. Types of conjugate systems. We can have double bond in conjugation with the double bond. That is pi conjugation. Pi bond can be in conjugation with the positive charge. Pi bond can be in conjugation with the negative charge. Lone pair, pi bond. Yes or no? All those possibilities you can write. Pi positive, pi negative, pi lone pair, pi free radical, pi, and this is negative. Wherever exclamatory mark is there, that is negative. So, and a lone pair or negative charge in conjugation with the positive charge or vacant orbital. So, we can also have lone pair or negative charge in conjugation with the d orbital. So, these are the different conjugations we can have. Double bond, the pi electron density can be in conjugation with the positive charge, or it can be in conjugation with the negative. Pi negative, pi positive, pi lone pair, pi free radical, pi. Negative charge or lone pair can be in conjugation with positive charge or vacant orbital. Negative charge or lone pair can be in conjugation with the d orbital. So let us look at different conjugations and different ways of writing the resonating structures. Let us start one by one. Electron movement. This is very important. Electron movement always occurs from negative charge or lone pair towards the pi electron density, from the pi electron density towards the positive charge. Negative charge or lone pair will be highly electron rich. From that only electron movement occurs. That movement will be in the direction of pi bond and from the pi bond to the positive charge. That is X double bond Y. The pi electron density can be in resonance or can be in conjugation with the Z atom which possesses positive charge or negative charge or lone pair or free radical. Pi can be in conjugation with positive or negative or lone pair or free radical. Let us look at all those perspectives now. So pi positive vacant orbital conjugation. So CH2 double bond CH2 plus. How we can write the respective conjugate system? CH2 double bond CH2 plus. We know from towards the positive charge from the pi electron density, the resonating structure can be drawn. So this resonating structure you can draw as CH2 plus CH double bond CH2. CH2 plus CH double bond CH2 and CH2 double bond CH2 plus, these two are resonating structures, and you can write the respective resonance hybrid as, the pi electron density is actually moving throughout all these carbon atoms with one of the carbon bearing a positive charge. So that will be a resonance hybrid. Allyl carbocation is actually stabilized by resonance hybrid, and the hybrid looks like this. Net charge must be same in all resonating structures. The net charge in all the resonating structures should be same, because if electrons are moving from one system, like a double bond to the positive charge, from the double bond electron density is lost, to the positive charge electron density is gained. So here we should get positive, the other side we should get neutral. So net charge must remain same throughout all the resonating structures. Is that clear how to draw the resonating structures for pi positive? This is a simple example, allyl carbocation. We'll change different examples now. Like we have a conjugate system like this. Can I say the pi electron density can be in resonance with the positive charge? So pi electron density can move away. If this pi electron density moves away, these two carbon atoms now get a double bond, and this carbon atom, if I say 1, 2, 3, the third carbon has seen the gain in electron density or not? Earlier, we have a pi electron density present between 1 and 2. Now the pi electron density is shared between 2 and 3. The third carbon, which has a positive charge, it gained the electron density. So positive charge on third carbon should be neutralized. Second carbon, earlier electron density shared between 1 and 2, now it is shared between 2 and 3. Second carbon has not seen the gain or not seen the loss. Earlier I am sharing the chocolate with friend 1, now I am sharing the same chocolate with friend 2. I will be getting my proportion always. Same thing here. Second carbon is not getting any charge here because it has shared the electron density between 1 and 2 earlier. Now also it is shared between 2 and 3. It is not getting any positive or negative charge. First carbon has seen the net loss in electron density because electron density moved away. So that is why first carbon will get a positive charge. So if you try to give numbering 1, 2, 3, so that is how you have to position the first carbon. These are important because whenever you try to expand a ring expansions we can do in most of the organic reactions. Ring expansions, ring contractions. There you should know to which carbon atom we have to assign the positive charge and how to perform the rearrangements. We'll discuss all those. If we have a structure like this, we can have what type of resonating structures? Positive charge can be present, like give the numbering 1, 2, 3. And I can write the resonating structure in this fashion. So I can say the 2, 3 pi electron density has been given to the 1, 3 now. So second carbon has seen the loss. So that will get a positive charge. Give numbering so that you can get an idea. So now 1, 2, 3. First carbon has positive charge, second has positive charge. Third can also be having a positive charge if you try to write the resonance in this panel. So 1, 2, 3. So all the 3 carbon atoms possess positive charge in one of the resonating structures, and the other 2 constituted a double bond. So how the resonance hybrid should look like? Resonance hybrid, how it should look like? Resonance hybrid should be looking like this. Yes or no? Where we have the positive charge and the pi electron density is under continuous rotation. Sorry. That means the pi electron density has a shade between these 2 carbons or the other 2 carbons with a positive charge bearing on the other one. So that is how your resonance hybrid will be looking like. Fourth one, if you try to write the resonating structures in the benzyl carbocation, how can write, students? The pi electron density can move away. So this carbon ortho position will be getting a positive charge. Then you can have a subsequent movement of electron density. You will get a para position positive charge. Then subsequent again movement of electron density. Then again you will get ortho position positive charge. Then the C double bond C pi electron density comes into CH2 will again regenerate its positive charge. So CH2 plus C6H6 will be the respective benzyl carbocation resonating structures. And how the resonance hybrid is looking like? Like we have the pi electron density completely revolving throughout, and we have a positive charge present on one of the carbon atom, like ortho or para. So this is going to be a respective resonating hybrid or resonance hybrid. Is that clear, students?
Yes, sir.
Okay, right. Resonance, pi negative resonance. The pi electron density can also be in resonance or in conjugation with the negative charge. How to write that? From the negative charge, you have to move the electron density towards the pi bond. From the pi bond, you have to move the electron density towards positive charge. That is how the motion of or direction of movement of electron density. So pi negative conjugation CH2 double bond CH, CH2 minus, CH2 double bond CH, CH2 minus. The negative charge comes into this pi electron density moves away. So you can write CH2 minus, CH double bond CH2. The allyl carbanion is also resonance stabilized. CH2, CH2 minus, like this structure will be in this fashion. Yes, right? So CH2 double bond CH, CH2 minus will have a respective resonating structure like this. And you will have resonance hybrid in this fashion. The pi electron density is actually moving. So I can indicate the motion of pi electron density throughout with the dotted lines and a negative charge present on the other carbon atom. So that can be indicated like this. CH2 double bond CH, CH2 minus. What is the hybridization of carbon in the given structure? What was the hybridization of the carbon in the given structure? What is the hybridization, sp2 or sp3? Or sp?
SP.
I think there's a lag, students. Just a second, I'll just refresh this. Yes, is it clear now?
Yes, sir.
Yes, right. Yes, try to answer this. CH2 double bond CH, CH2 minus. What is the hybridization of carbon in the given structure?
sp3.
sp3 or sp2? Yes, Shima.
Sir, sp2.
Why Suman?
Sir, that minus charge will be in resonance with double bond.
Yes, very good. Whenever you have a negative charge involved in resonance, that negative charge will be coming into pi electron density moving away. So we'll be having CH2 minus CH double bond CH2. In this case, what you can say? In this case, what you can say? The negative charge which is involved in the resonating structure, that is not involved in the hybridization, because hybridization will never form double bonds or pi bonds. So this is CH2 minus CH double bond CH2. So is the respect to resonating structure. So hybridization is sp2. Yes, Shima, you can speak. I have given access to all the students. Okay, you can just ask if you have any doubts. Right. So note, lone pair taking part in resonance is not considered for hybridization. Lone pair taking part in resonance, that is not considered for hybridization, because it will be leading to the formation of pi bond. So lone pair taking part in resonance, they were considered as the pi electrons. So hybridization or hybrid orbitals will never form pi bonds. Right. Try to write the resonating structure here: CH2 double bond CH O minus. Shima, I have given the access to everyone. From here, I have not restricted you to not to speak. Just rejoin again so that you can speak out. Write the resonating structure here: CH2 double bond CH O minus. The negative charge will be coming into pi electron density moving away. So if you try to write the subsequent resonating structure, we have CH2 minus CH double bond O. CH2 minus CH double bond O, that will be the respective resonating structure. So you may get it out, sir, you are writing this resonating structure, but is it stable or not? Like negative charge or more electronegative atoms is more stable. So CH2 double bond CHO minus, it should be more stable. Yes, that is based on stability, we can say. I am writing all the resonating structures. Although you have written a lot of resonating structures, all the resonating structures will not have same stability. The stability of resonating structures were decided based on some set of rules, which you are going to study just after writing the resonance structures. This negative charge cyclopentadienyl carbon ion. So negative charge can come into pi electron density, can move away. So negative charge, if it comes into pi electron density, can move away. So generating this type, negative charge can come into pi electron density, can subsequently move away. Negative charge can come into pi electron density, again can move away. Negative charge can come into pi electron density, subsequent move away. Finally, negative charge coming into pi electron density moving away. So you will be getting all types of resonance structures. So pi electron density is completely moving away, and you have negative charge at one of the carbon atom. So those were the resonating structures in cyclopentadienyl carbon ion. Is that clear, students?
Yes, sir.
These resonating structures, writing the resonating structure is very, very important, because then only we'll get to know what type of reaction it is going to happen whenever we are doing any organic reaction. So benzyl carbon ion, we have C6H6, C6H5 group connected with CH2 minus. Negative charge comes into pi electron density moving away. Again, negative charge coming into pi electron density moving away. Negative charge coming into the pi electron density moving away. Negative charge coming into pi electron density moving away. And resonance hybrid will be in this fashion. This is also the resonating structure, final resonating structure. And ultimately you have resonance hybrid where you have the total pi electron density moving and negative charge present. So benzyl carbon ion, whenever we have been given with benzyl carbon ion, the negative charge, from the negative charge, the movement of electron density occurs towards the pi electron density. Then pi lone pair conjugation. The pi electron density can also be in conjugation with the lone pair. So how the pi lone pair conjugation can be written? Vinylamine, if you take the lone pair of electrons and nitrogen, they can come into pi electron density can move away. So we get CH2 minus CH double bond NH2. And now we have to think carefully. This carbon, like if I give numbering 1, 2, 3, the first atom nitrogen has seen the loss or gain in electron density.
Loss.
The loss, because lone pair of electrons are present only on nitrogen earlier. Now they have been shared between nitrogen and carbon. So nitrogen has seen the loss in electron density, so it will be getting a positive charge. Second, earlier it was sharing the electron density, pi electron density between 2 and 3. Now it is sharing between 1 and 2. So second has seen no loss, no gain. But third, the pi electron density has been given to third. So if I give numbering like 1, 2, 3, the third atom has seen the net gain. So this will be your respective resonating structure. CH2 minus CH double bond NH2 plus CH2 minus. So this is not the correct resonating structure. CH2 minus CH double bond NH2 plus. That will be the right resonating structure. The second way, if you think of phenol, lone pair of electrons and oxygen comes into pi electron density moves away. So you have negative charge at the ortho position. The negative charge can come into pi electron density can again subsequently move away. You can have negative charge at para. Negative charge coming into pi electron density again moves away. Negative charge comes into pi electron density moves away. So oxygen, if you look carefully, oxygen has 2 lone pairs of electrons on itself. Now the lone pair of electron oxygen has been shared between oxygen and carbon. That means electron density moved away from oxygen. So oxygen has seen the loss in electron density. So that is why it has a positive charge. And ultimately you will have the same phenol structure, but now the positions of double bonds has been changed. Is that clear how to write the resonating structures in pi lone pair, pi positive and pi negative?
Yes, sir.
Yes, right. Pi free radical conjugation. The pi electron density can be in conjugation with the free radical. How is that possible? CH2 double bond CH CH2 dot. Whenever we have a free radical, you have to assume it like this. CH2 double bond CH CH2 dot means the pi electron density you can treat as 2 electron, right? The 2 electron you have to give 1 electron to this carbon, other electron to the other carbon. So you can imagine that like CH2 dot CH dot CH2 dot. You don't need to write the structure, but you just imagine, okay? That means these 2 electrons, free electrons, are now going to be paired up, forming CH2 dot CH double bond CH2. So this structure and this structure, they are resonating structures. That means wherever you have a pi bond, 1 electron you give to this carbon, other electron you give to this carbon. Whatever the free electron on this carbon present, that will combine with the other free electron on the other carbon to form a pi bond. And this terminal carbon get only 1 electron. So allyl free radical is also stabilized by resonance. CH2 double bond CH CH2 dot gives CH2 dot CH double bond CH2. That is the resonating structure in allyl free radical. That is the resonating structures in allyl free radicals. Here also I can write the wherever the double bond I have, that I can shift in this fashion. Like 1 electron I can give to this carbon, the other electron I am giving to the other carbon. So that I will be getting double bond CH2 and this particular electron will get a free radical now. Same way again you can try to write the resonating structure. Now ortho and para positions will get a free radical electron. Same way I can do. This electron given to this carbon, that will pair up with the other electron to form a double bond. Again I'll be getting this type of resonating structure. Again I can just use the electrons to each carbon atom bearing a double bond in the final case, generating this particular free radical. whenever you have a positive charge, like CH2 plus C6H5, benzyl carbocation means ortho para positions will have positive charge. Benzyl carbonyl means ortho para positions will get negative charge. Benzyl free radical means ortho para positions will get free radical electron. You should concentrate carefully in the resonating structure at every ortho and para. The effect is seen, either positive charge or negative charge of free radical. Okay. So mesomeric effect is only possible, or the resonating effect is only possible at ortho and para positions. If we have a substituted meta position, it will not show mesomeric effect. That is the point which you can understand, and which we will be discussing in the upcoming slides as well. Pi-pi conjugation. Pi bond can also be in conjugation with pi bond. CH2 double bond CH, CH double bond O. This pi electron density can come into this C double bond O, pi electron density can move away. So now I'll give numbering 1, 2, 3, 4. You have to assign charges. First carbon will get what charge? First carbon will get what charge?
Positive charge.
Second and third.
Neutral.
Where is the double bond now?
Between second and third.
Between second and third. What about oxygen?
Negative.
Negative charge. Very good. So first carbon will get a positive charge, CH2 plus, CH double bond CH O minus. So this is nothing but acrolein or acraldehyde. Acrylaldehyde. Movement of electrons towards more electronegative atom will be seen obviously. The movement of electrons, you can also write, sir, if I want to write the resonating structure in this fashion, CH2 double bond CH, CH double bond O. You can write, there is a possibility the electron density can also move in this fashion. This pi electron density can move away, generating what? Negative charge on this particular carbon, CH double bond CH, single bond oxygen. Oxygen will now have a positive charge. Oxygen already has 2 lone pairs. We all know oxygen has 2 lone pairs, but this electron density has moved away from oxygen, right? Because of that, the oxygen gained a positive charge. But you can say this is one of the resonating structure, that is for sure. But the only logic is, this is one of the resonating structure, but this resonating structure is not a stable, because movement of electrons is away from the more electronegative atom. CH2 double bond CH, CH double bond CH2. So same type of resonating structure you can draw. This pi electron density can be moving to the next bond, and that C double bond C pi electron density given to the terminal carbon, generating CH2 plus, CH double bond CH, CH2 minus. Both are same only, yes or no? If I try to move in the other way, other fashion also, both are going to be same, because everywhere we have a carbon atom only. Until unless I place this carbon as C13 and this carbon as C14, then I'll say C13 has positive charge, C14 has negative charge. Here C14 has positive charge, C13 has negative charge. If you try to change the motion of electron density, if I move the electron density in this fashion, C13 will be having a negative charge, C14 will have a positive charge. If I do the electron density movement in the above fashion, C14 will have a negative charge, C13 will have a positive charge. And in benzene, you can just try to write the resonating structures. The pi electron density can subsequently move in this fashion, generating the respect to benzene. These are the 2 resonating structures of benzene. These are all pi-pi conjugations. These are all pi-pi conjugation systems. Then we have benzaldehyde. This is also pi-pi conjugation. The pi electron density can move this fashion. The pi electron density can be moving towards oxygen. In this way, you will get a negative charge on oxygen. C double bond system. This carbon get a positive charge. Subsequent movements, you get para position positive charge. Subsequent movement, ortho again positive charge. This negative charge comes into this pi electron density moves into. Now we'll get the same type of CHO group, but change in the positions of double bonds. So these are the respective resonating structures in benzaldehyde. These are the respective resonating structures in benzaldehyde. Is that clear?
Yes, sir.
Yes.
Clear, right? Now A bond with B. Manasi, where in which example you're talking about the moment of the difference in electronegativity is 0?
The
And if you
previous one.
the previous one, and I'll ask a simple question, Mansi. Is the resonating structure is due to difference in electronegativity? First question.
No, sir.
So then why you are asking like difference in resonating structure is not due to difference in electronegativity, it is due to conjugation. Okay.
Sir, you said that in this example that when pi and pi are in conjugation, then the electron density will be moving away from
Towards,
the.
yeah, I
Yes.
understand. Electron density, whenever there are two atoms like CH2 double bond CH, CH double bond O, the electron density can move in this fashion, one possibility. The electron density can move in the other fashion, other possibility, same example which we have seen. When we have two different types of atoms, when compared to this movements, this is more preferable. But the movement of electron density is not due to electronegative difference. Understand this carefully. In the resonating structures, whatever you are trying to draw, they are not obtained due to difference in electronegativity. They were written due to conjugation presence. If I try to write a resonating structure, if I try to write my compound in this fashion, CH2 double bond CH, CH2, CH double bond O. So oxygen is more electronegative. Can I move these electrons, pi electrons now? Oxygen is more electronegative. I'm agreeing with this oxygen. Oxygen is more electronegative. But can I move the pi electrons directly like this?
No, sir.
This is not possible. So even though you have more electronegative atom, the movement of a pi electron density towards more electronegative is only possible when there's a conjugation system. And whenever you're trying to compare two moments, movement of electron density towards more electronegative atom is more stable when compared to the movement of electron density towards less electronegative atom. Understood now? So conjugation is the main role. If there is a conjugation, then only we can have possibility of resonance. No conjugation, no resonance.
Therefore,
Right?
sir, we choose the electronegative structures to show the stability in resonance
Yeah.
hybrid.
Yeah, as of now, I'm not saying any stability. We are just writing all the possible resonating structures. Once this resonating structures writing for all the cases has been done, we'll look at stability. Like we have written, resonance hybrid will be there, and every resonating structure is contributing to resonance hybrid. So if which structure contributes more, which structure is more stable, that contributes to the more. So how to decide the stability of resonating structures? There are some set of rules. Based on that rules, we'll study it. Okay. Whenever
Yes.
we have equivalent resonating structures, their contribution is same. Like for benzene, these two are equivalent. So it will contribute 50%. The other form is also contributing 50%. But whenever I say CH2 double bond CH, CH double bond O, acrylaldehyde, in that case, this will contribute more contribution to resonance hybrid because it is more stable. More contribution to resonance hybrid. Got it now? So there are some set of rules based on which you have to decide which resonating structure is going to be more stable. That was a very good question. Fine.
Thank you, sir.
Okay, fine. So now we can have AB. So lone pair or negative charge can also be in resonance with the positive charge or vacant orbital. So CH3 O CH2 plus. So negative charge, positive charge and lone pair of electrons, they were in resonance, and you can write what type of resonating structure. The lone pair of electrons and oxygen, they can come into, we can say CH3. Oxygen, we have two lone pairs earlier, now we have only one lone pair. Oxygen and carbon has single bond earlier, now we have a double bond. And this carbon with a positive charge is gained the electron density, so it becomes CH2. The other lone pair on the oxygen has been involved in the bond formation. So net electron density on oxygen decreased, so oxygen has a positive charge. So among these two resonating structure, which is more stable? Just for asking. If you think logically, CH3 oxygen with the lone pair and positive charge double bond CH2, CH3 oxygen with two lone pairs and CH2 plus.
Oxygen with two lone pair will be more stable.
Why, Sapna?
Positive charge on more electronegative.
Okay, this is more stable actually. In reality, this is more stable. Oxygen with the positive charge and CH3O with lone pair positive charge double bond CH2, that is more stable, because whenever you are trying to compare the stabilities of resonating structure, the first priority has to be given to all the atoms in that particular compound should have octet electronic configuration. If you look at this particular scenario, here carbon has CH3O, CH3CO, that means 4 bonds are there, so carbon has 8 electrons around itself. Oxygen, 2 bond pairs, 2 lone pairs, so 8 electrons around itself. This carbon, carbon-oxygen bond and 2 CH bonds, only 6 electrons around itself. But look at the structure, CH3O, CH3CO, 4 bonds, that means 8 electrons. Oxygen, 1 lone pair and 3 bonds. So 3 bond pairs means 6 electrons, 1 lone pair again 8 electrons. CH2 double bond C, CH2 double bond O. So double bond means 4 electrons, CH2 means again 4 more electrons, so 8 electrons. So every atom, if it contains a octet electronic configuration, except hydrogens, because hydrogen can never have octet, it will only have duplet. So if every atom in the resonating structure possesses octet electronic configuration, that is more stable. So CH3CO plus with a lone pair double bond CH2 is more stable. Whatever the rule we are saying, that more electronegative atom should contain negative charge, more electronegative atom possessing positive charge is less stable. That has to be checked after your octet. Octet has the highest priority. Okay, so that is why it is more stable. So we look at all the stabilities, just an idea. You should know, you should have some idea. So CH3 nitrogen containing lone pair and CH2 plus lone pair of electrons and nitrogen, they can come into. If they come into, what happens? You will get CH3 nitrogen will now have a positive charge and double bond CH2 plus. Again, if you try to compare here in this particular resonating structure, you have octet or not, octet present or not. Earlier you have only 6 electrons on this carbon. This nitrogen has 1, 2, 3, 4. That means 3 bond pairs, 1 lone pair, 8 electrons. This carbon has 4 bonds, so 8 electrons. What about here? Carbon has 4 bonds, 8 electrons. Nitrogen 1, 2, 3, 4, 4 bond, 8 electrons. This carbon also has 8 electrons. So which should be more stable? This should be more stable. The first rule is we have to check the octet electronic configuration, like 8 electrons should be present around all atoms in the resonating structure. If that is present, that resonating structure is more stable. Clear? Negative or positive charge or free radical or lone pair on double bond atom in the ring does not take part in resonance. They are said to be localized. That means if you have a scenario like this, negative charge or positive charge or free radical or lone pair on atom, like they are not in resonance, because adjacent subsequent pi electron density, they were in resonance, but negative charge or positive charge or free radical or lone pair of electrons, they were not present in delocalization, they were not involved in delocalization. They are said to be localized. Understood this? Negative, positive, free radical, lone pair on double bonded atom in ring does not take part in resonance. They are said to be localized. Is that point clear?
Yes.
Yes, right. Try to answer this question. In which of the following compound, lone pair is localized? In which of the following compound lone pair is localized?
Aniline.
Aniline lone pair is localized. Aniline lone pair. Imidazole, it has 2 nitrogens. Which lone pair is actually, like, which nitrogen's lone pair is actually in localization and delocalization, that you have to think of. First, benzylamine. Is that localized or not? Check carefully, benzylamine.
No.
The lone pair of electrons and nitrogen, they were not involved in CC double bond. So if you look at this lone pair of electrons in this nitrogen, that can be involved in resonance, that is delocalization. But lone pair on this nitrogen, that is not involved in resonance. That means this is localized, this is delocalized. What about this? Delocalized. What about this? Delocalized. First one is localized. So we can have this type of solution. So first compound, lone pair of electrons and nitrogen localized because no conjugation present. If you look at sp2, like nitrogen involved in the double bond, that nitrogen having a lone pair, that is localized. The other nitrogen bearing a lone pair, that is actually delocalized, which is involved in delocalization with the adjacent pi electron density resonance. C6H5NH2 unlane, the lone pair of electron nitrogen delocalized, and here also the lone pair of electrons and nitrogen are delocalized with the pi electron density. Clear? Try to answer simple question. Which is more acidic? CHCl3, CHF3. Which is more acidic? CHCl3, CHF3.
So CH.
Why, Suman?
So because d orbital resonance in CCl3.
Very good. So CHCl3, if it undergoes loss of H plus ion, you will be generating CCl3 minus. If it undergoes, if CHF3 undergoes loss of H plus, it forms CF3 minus with a negative charge on carbon. So the negative charge on carbon and a chlorine has 3 lone pair of electrons, 3 chlorines. But a chlorine also has a vacant d orbitals. But a fluorine do not have any vacancy. Fluorine do not have any vacant d orbitals because 2d subshell itself is not present. So negative charge on carbon that can be going into the resonance. So here we can say CHCl3 or CCl3 minus has negative d orbital resonance. D orbital resonance. If you apply a lone inductive effect, that will be leading to CHF3 going to be more stabilized. If you apply inductive effect, what you'll say? CF3 is there, and we have a carbon hydrogen bond. Fluorine is more electronegative. Because of that more electronegative nature of fluorine, all the 3 CF bonds, they are going to be becoming more and more polar, generating more positive charge on carbon. So this acidic, this CH bond becomes more acidic. So cleavage will be easily happening. But inductive effect is less dominant when compared to resonance. So CHCl3 should be more acidic because CCl3 minus is going to be resonance stabilized. Right? Very good, Suman. So stability, this is what I'm talking about. Stability of resonating structures. So rules for deciding stability of resonating structure. A resonating structure having octet complete of all atoms. If all the atoms contain octet electronic configuration, of course, except hydrogen, because hydrogen can never have octet, it will have only 2 electrons around itself, duplet. Resonating structures having octet configuration for all the atoms, that is more stable. Like structure 1, CH2 double bond CH, CH double bond CH2. Structure 2, it's the respective resonating structure which is obtained by pi-pi conjugation. CH2 plus CH double bond CH, CH2 minus. Now try to look at octet. This carbon has 2 plus 2, that is 4 bonds are there, 8 electrons. Every carbon involved in 4 bonds. If you look at the first structure, so 1, 2, 3, 4, every carbon involved in 4 bonds. So 8 electrons are present on every carbon. But in the second structure, this carbon has a positive charge. So it is like a only involved in 3 bonds, carbocationic carbon. So only has 6 electrons. So remaining all other has 4 bonds, and here you have carbon ion, so 8 electrons. So there is CH2 plus here, which do not have octet electronic configuration. Because of that, structure 1 is more stable when compared to structure 2. Structure 1 is more stable when compared to 2 because in 1 we have every atom possessing octet. CH3O CH2 plus, this is what the example we have given earlier. This one, if you look at in the first structure, you have 8 electrons and 6 electrons. In the second structure, you have 8, 8 and 8. So every atom possessing octet, that should be more stable. So second structure is going to be greater, more in stability when compared to first structure. If you look at CH3O CH2 plus and its resonance structure CH3O double bond CH2. Got it or not, all of you?
Yes, sir.
Right. Non-polar resonating structure. Non-polar resonating structure means uncharged. That is more stable than the polar resonating structure are charged. Like if you have CH2 double bond CHCl, and if you try to write the resonating structure like pi electron density and the lone pair. Pi lone pair conjugation, from the lone pair towards the pi electron density movement occurs. So lone pair of electrons on chlorine, they come into pi electron density, subsequently move away. So generating CH2 minus CH double bond Cl plus. Look at this atom. Carbon involved in 4 bond, 8 electrons. This carbon already involved in 4 bonds, 8 electrons. Chlorine 1, 2, 3, and 4. That is again 8 electrons. 3 lone pairs, 1 bond pair. Here this carbon has CH2 minus 3 bonds and negative charge, 8 electrons. This carbon 4 bonds, 8 electrons. This chlorine 2 bonds, 2 lone pairs, 8 electrons. So every atom has octet now. In the two resonating structures, every atom has octet electronic configuration, but the only difference is charge. So both the resonating structures have octet electronic configuration for all the atoms. The difference between the resonating structure is just the charge. And I have given the example non-polar resonating structure. Non-polar resonating structure means uncharged resonating structure that is more stable than the polar resonating structure or charged. So which you can say first structure is stable when compared to second, or this is stable when compared to this. Right? Whenever both the atoms, whenever you have both the resonating structures possess octet same, this is applicable only when octet electronic configuration is satisfied. Whenever both the resonating structures have octet for all the atoms, and if one is charged, other is uncharged, then you can say uncharged is more stable when compared to charged. Why? What was the reason behind like uncharged is more stable when compared to charged? Because separation of charges requires energy. The separation of charges requires energy, thereby decreasing stability. If both the resonating structures are charged, then resonating structure in which negative charge is on more electronegative atom and positive charge on less electronegative atom is more stable. This is applicable only if octet is complete on all atoms. If octet is complete on all atoms. CH2 minus CH double bond O, CH2 double bond CHO minus. Like you have 8 electrons, 8 electrons, 8 electrons, 8, 8, and 8. This carbon also has 8 electrons, this also 8 electrons, oxygen also has 8 electrons. Because 1 bond, 2 lone pairs and negative charge. So 2 lone pairs includes 4 electrons, 1 bond includes 2 more electrons, negative charge includes 2 more electrons. So every atom has 8 electrons. So both the resonating structures are charged, and in both the resonating structures, every atom possesses octet. In that case, you have to check negative charge on more electronegative is more stable when compared to negative charge on less electronegative. So you can say 2 resonating structure 2 is more stable when compared to resonating structure 1. Okay, this is applicable only if octet is complete on all atoms. This is important because if you apply only this more electronegative should contain negative charge, then you will get wrong in other cases. Why? Because octet rule you have to check. Okay. Resonating structures in which unlike charges are at minimum separation or like charges are at maximum separation are more stable. Reason? Because charge separation requires energy. Charge separation increases potential energy. Charge separation requires energy. So if you have unlike charges, the unlike charges should be separated by very small distance. If you have like charges, if both are positive charge, then they should be separated by maximum distance. Because like charges will repel, unlike charges will attract, right? So lone pair of electrons and oxygen coming into, so pi electron density subsequently moving away, negative charge at ortho. Write down all the resonating structures, you will get negative charge coming into pi electron density moving away. You will get third structure, that is para position negative, again ortho negative. Again you will be having phenol, but just a change in the position of double bonds. More stable resonating structure have more contribution to the resonance hybrid. Which will be more stable here? If you try to compare 1, 2, 3, 4, 5. Which structure should be more stable?
1 more stable than 2 and 4.
1 and 5 are the equivalent, Faizan? 1 and 5?
Yes. Yes, sir.
Because in all the resonating structure, every atom has octet. If you look carefully, every atom has octet electronic configuration. Octet is satisfied for all the atoms. You check out any structure. Like I'm taking this oxygen, lone pair is there, C double bond C, O double bond C, So 2 plus 1, 3 bonds and 1 lone pair, so 8 electrons. This carbon 4 bond, 8 electron. This carbon CH bond and 3 bonds, 4 bonds, 8 electrons, 4 bonds, 8 electrons. This carbon 2 bonds plus 1 CH bond, 3 bonds plus negative charge, 8 electrons. So every resonating structure has octet for all the atoms. So uncharged resonating structure are more stable when compared to charge. So 1 and 5, they are going to be equivalent. After 1 and 5, which are going to be more stable?
2
Can I
and
say
4.
2 and 4? Because negative charge and positive charge, they should be separated. That is, unlike charge should be separated by minimum distance, like charges should be separated by maximum distance. So 1 and 5 will have equal stability, then 2 and 4, and then least stable is going to be 3. So 1 and 5 contribution to the resonance habit is more, then 2 and 4 contribution, then the contribution of 3 will be least. That is how you can understand the order of stability. Order of stability of resonating structures. Compare here, more stability, compare stability of a resonating structure. So here we have RC double bond H, RC double bond OH. Oxygen has lone pair of electron, negative charge. Like lone pair of electrons and oxygen comes into, pi electron and moves away. If you try to write down that, you'll get R, C, O. Oxygen has 2 lone pairs and negative charge. C double bond, oxygen 1 lone pair, positive charge, and CH. The second structure, whatever they have given, that is not possible. That is not a possible resonating structure. This is the second. This is the first structure given to you. This is the second structure. Third structure and fourth structure are possible, because third structure is R C double bond O, pi electron is moving away towards just oxygen, C double bond O resonance. So carbon will have positive charge, oxygen will have 2 lone pairs and negative charge. This OH is as it is. Fourth structure, same, but the electron density now moving towards carbon. So R, carbon will have negative charge, oxygen will have positive charge, and we have OH. Now try to compare the stability A, B, C, D. That is, this is your structure A. 1, 2, 3, 4, or A, B, C, D, whatever it is. A, B, C, D. Compare the stabilities of A, B, C, D resonating structures. R, C double bond OH is A. R, C, O minus C double bond O, positive OH bond. First you have to check what? First you have to check the octet electronic configuration. If your octet is satisfied by all the atoms, that should be given the higher priority. If octet is not satisfied by some of the atoms, that should be given the lesser priority. Look at the C and D. R, C plus.
A is more stable.
Yes, please.
A is more
Yes, C and D, if you compare, the carbon has a positive charge. So around this carbon, octet is incomplete. In D also, you have positive charge on oxygen. The pi electron density moves towards carbon. So octet is incomplete in C and D. Look at A and B. Octet is complete or not? A and B, octet is complete for all atoms. A and B, octet is complete for all atoms. C and D, octet is incomplete. And if you try to compare among C and D, octet is incomplete and negative charge on, more electronegativity is slightly more stable. So C should be more stable when compared to D. Among C and D. Among A and B, which should be more stable? Octet is complete for all the atoms. If octet is complete for all the atoms, then uncharged resonating structure is more stable. So A is complete octet and uncharged. B is complete octet but charged. C and D incomplete octet, but C has more electronegative atom, negative charge. D has less electronegative atom, negative charge. So what should be the order now?
A, B, C.
A, B, C, D.
A, B, C, D, right? So complete octet non-polar, complete octet polar, incomplete octet with negative charge on. So correct order should be A, B, C, D. A should be greater, then B, then C, and then D. Complete octet and non-polar, complete octet and polar. Incomplete octet with negative charge and more electronegative. Incomplete octet with negative charge and less electronegative. You should not directly jump to this C as more stable, because here carbon do not have octet. Octet is given high priority, then only negative charge and more electronegativity is given more priority. Try to compare stability of resonating structures. Complete octet. here A and B have octet, but C compound C, if you look at this carbon has positive charge, CH bond, carbon bond, carbon chlorine bond, 3 bonds, only 6 electrons are there, incomplete octet. A and B have complete octet, yes or no? This atom carbon 8 electrons, this carbon 8 electrons, the chlorine also 8 electrons around itself. 8, 8 and 8. A and B complete octet, C is incomplete octet. So A and B should be more stable when compared to C. And among A and B, which should be more stable? Complete octet means uncharged should be more stable. Yes or no? So A complete octet non-polar, B complete octet polar, C incomplete octet. So A greater than B greater than C. That will be the right order of your stabilities for the respective resonating structures. Is that clear, students?
Yes.
Bond length comparison. You compare CH3, CH2Cl, CH2 double bond CHCl, and C6H5Cl, where the bond length is high. Like arrange L1, L2, L3. In CH3, CH2Cl, L1 is the bond length of carbon chlorine bond. CH2 double bond CHCl, L2 is the bond length in carbon chlorine bond. PHCl or C6H5Cl, L3 is the bond length of carbon chlorine bond. Where the bond length is high?
L1 highest.
L1, if you L1, if you look at, there is no resonating structure. L2, you look at, the negative charge is going to be developed on this particular carbon because lone pair of electrons and chlorine coming into. If you look at L3, the lone pair comes into pi electron and moves away. The negative charge comes into pi electron and again moves away. The negative charge comes into again the moment of pi electron and the negative charge comes into again the moment of pi electron and If you look at the resonating structures, like if you look at first compound, second compound, and third compound, in first compound, carbon chlorine bond is not having any double bond character. In second compound, carbon chlorine bond has double bond character. In third compound, carbon chlorine bond has more double bond character because out of 5 resonating structures, 3 resonating structures have double bond between carbon and chlorine. So double bond character is highest. In third one, double bond character is highest. If double bond character is highest, the bond length that is going to be least. Here double bond character is present. Okay. Double bond character is present. But we cannot say that double bond structure is going to be more stable because the first structure uncharged and octet is more stable. Here, no double bond character. No double bond character is available in the first structure. Second and third, you have double bond characters. Third structure has the highest double bond character. So L3 will be the shortest bond, then L2, then L1. L1 is greatest, then L2, then L3. This is the order. That means L3 is going to be least. Right. Let us start with the next concepts. Aromaticity. Aromaticity means there are 3 types of structures: aromatic, anti-aromatic, and non-aromatic. Aromatic means what? 4 conditions you have to satisfy. Cyclic, compound should be cyclic. Complete conjugation, planarity, and 4n plus 2 pi electrons. That is aromatic. Cyclic, complete conjugation, planarity, 4n pi electrons. Instead of 4n plus 2, if you have 4n pi electrons, then that is anti-aromatic. If any one condition of aromatic nature or non-aromatic nature, of aromatic nature or anti-aromatic nature is not satisfied, that is not 4n plus 2 pi electron or 4n pi electron or non-planar or acyclic, in that case you will be getting non-aromatic compounds. Right? 4 conditions: cyclic, complete conjugation, planarity, and 4n plus 2 pi electron should be satisfied for aromatic. 4n pi electron should be satisfied for anti-aromatic. So compare the stabilities now: aromatic, anti-aromatic, and non-aromatic. Which should be more stable? Aromatic compounds are highly stable. Then after aromatic we'll have which are more stable?
Non-aromatic.
Non-aromatic. Very good. After aromatic, non-aromatic are more stable and anti-aromatic are highly unstable. We have to understand this concept carefully. Aromatic, non-aromatic, anti-aromatic. I'll apply this concept to one example now. To try to compare the basic nature here. Among these two compounds, which should be more basic? First, check out lone pair of electrons and nitrogen. Lone pair of electrons and nitrogen, they were in resonance, they were in delocalization. Yes or no? They were in delocalization. Pi electron is moving away. And nitrogen, both the nitrogens, they are involving the single bonds only. After resonance, you can just say again the lone pair of electrons comes into, then double bond is formed. So you can have this lone pair is not going to be involved in the hybridization. So sp2 hybridization, nitrogen possess. Right. Now try to compare which is going to be more basic. Which compound, compound A or compound B, and why? Give the answers. Only two options, A and B. You can say A or B. But reason you have to think of. What is the reason? Like if I try to attack the H plus ion from the lone pair of electrons in the first compound, the lone pair of electrons and nitrogen from the first compound, if they attack H plus ion, they'll generate this structure or not? Nitrogen will have two NH bonds now, and it will have a positive charge, and will have this structure. If the lone pair of electrons and nitrogen, if they attack the H plus, they'll form this structure, NH3 plus. Now I am saying this is a base. For every acid, there will be respective conjugates. For every acid, there will be respective conjugate base. For every base, there will be respective conjugate acid. Suman says option A. Option A is more basic or less basic, Suman?
Sir, more, I guess.
Why?
Sir, after getting involved in that conjugation, it will gain it aromaticity.
Aromaticity gained or lost? It becomes aromatic or anti-aromatic? Check out carefully. It is aromatic or anti-aromatic? This particular compound. After the lone pair of electrons and nitrogen attack the H plus, it becomes 4n pi electron.
Oh, got it. I thought it wrongly.
Okay. So the compound A, after attacking the H plus, it forms this type of structure where it has plenarity is there, cyclic is there, complete conjugation is there, and it has 4n pi electrons. Like 4 pi electrons are there. 4 pi is equals to 4n pi means n is equal to 1. So 4n pi electrons is there in this particular compound. So in compound A, whatever the conjugate acid you have, for every base you will have respective conjugate acid. The conjugate acid is anti-aromatic in nature. That means conjugate acid is highly unstable. If conjugate acid is highly unstable, the base, why will it attack the H plus? No. That means base is not attacking the H plus to form a conjugate acid. So this is going to be the weakest base. Weakest base or poor base. So like that, the application of aromatic nature and anti-aromatic nature, that has to be clear. Anti-aromatic compounds are highly unstable because of repulsions, and they won't exist in the monomer fashion. They also have a tendency to form a dimers. Like if I give a compound like this to you, this will actually exist. This is cyclobutadiene that will actually exist in the form of a dimer like this. Okay, dimerization occurs. Cyclobutadiene exists in the form of a dimer because of anti-aromatic nature. It is highly unstable, and that is why it will form dimer. Non-aromatic compounds, which are neither aromatic nor anti-aromatic, they are said to be non-aromatic compounds. Stability order: aromatic compounds greatest, then non-aromatic, then anti-aromatic. Note: anti-aromatic compounds are highly unstable and do not exist at room temperature and having tendency to make a dimer. This is what I have told you. If I have any anti-aromatic compound, yeah, same example, cyclobutadiene will form a respective dimer like this because they are highly unstable in nature. I'll be giving different examples. Find out whether the compound is aromatic, anti-aromatic, or non-aromatic. Benzene. We all know benzene is 4n plus 2 pi electrons. 4n plus 2 pi electrons. Plenarity, because every carbon is sp2 hybridized. Plenarity, complete conjugation. complete the conjugation, and cyclic, all the conditions are satisfied, so benzene is going to be aromatic.
Aromatic.
Right, very good. Complete conjugation, 6 pi electrons, Huckel's rule satisfied, so aromatic. What about cyclopropenyl cation? Find out whether the compound is aromatic, anti-aromatic, or non-aromatic.
Aromatic.
Aromatic, right? Because you have complete conjugation is there, and 2 pi electrons are available. 4n plus 2 is equals to 2 when n is equal to 0. So 2 pi electrons, complete conjugation, aromatic. Complete conjugation, 2 pi electrons. So the compound should be aromatic in nature. Find out whether the compound is aromatic, anti-aromatic, or non-aromatic. Cyclopropenyl anion,
Non-aromatic.
non-aromatic or anti-aromatic.
Anti-aromatic.
4n is equals to 4n pi electrons is equals to 4. So n should be is equals to 1. So 4 pi electrons are there because this negative charge also comes into. Whenever you have negative charge, you have to treat that as 2 electrons. Whenever you have a double bond, you have to treat that as again 2 more electrons. So negative charge also including the pi electrons. So 4 pi electrons is equals to 4n pi, n is equal to 1. Complete conjugation, aromatic, complete conjugation, plenarity is there, and cyclic, so anti-aromatic in nature. What about this? This I have just now given the example. Aromatic or anti-aromatic or non-aromatic?
Anti-aromatic.
Anti-aromatic. Cyclobutadiene is anti-aromatic. That is why it will form a dimer. And this is a very, very interesting example. Whenever you are having a 4-membered cyclic transient state, can you just say any reaction where we have a 4-membered cyclic transient state as an intermediate? If you think of hydroboration oxidation, in the hydroboration oxidation, 4-membered transient state is intermediate. Like that, there are some set of reactions where you are having 4-membered transient states. And in that 4-membered transient states, if you look carefully, if there is a possibility of anti-aromaticity, that is not going to be the right reaction path. We look at all the reactions also, just to study the GOC concepts carefully first. This is anti-aromatic because 4n pi electrons, 4 pi electrons. What about this? Cyclopentadienyl carbanion. 2 pi bonds and 1 negative charge, that is 6 pi electrons. Cyclic, complete conjugation, plenarity is there. Huckel's rule satisfied, cyclic is there, plenarity complete, and complete conjugation. So aromatic or not?
Yes.
Yes or no? 6 pi electrons, all these are satisfied. What about this compound? Cyclopentadienyl carbocation. Pi electron density moving. So 4 pi electrons are there. How many pi electrons? Complete conjugation, 4 pi electrons.
Anti-aromatic.
Cyclic, anti-aromatic in nature. So anion, whenever it is there with the 5-membered ring, there is a possibility cyclopentadienyl carbanion because it has 6 pi electrons. Cyclopentadienyl carbocation, it has only 4 pi electrons, so anti-aromatic. What about furan? Lone pair of electrons can be in resonance, yes or no? So how many pi electrons are there? So you can write them respective resonating structure in this fashion. Oxygen 1 lone pair, C double bond O, positive charge, negative charge here, double bond here. So 1, 2, 2 double bonds and negative charge. So you can say 6 pi electrons. 6 pi electrons, complete plenarity, complete conjugation and cyclic. So it should be aromatic in nature. Complete conjugation, 6 pi electrons. So aromatic. Furan is aromatic in nature. Thiophene, same aromatic or not? In the same fashion, I can move the electron density of sulfur, the lone pair of electrons and sulfur into resonance with the pi electron density. Sulfur will now has only 1 lone pair and a positive charge. Double bond positions are going to be present like this. Again, we have 6 pi electrons, complete conjugation, plenarity and cyclic. So it is also going to be aromatic in nature. Pyrrole is aromatic or anti-aromatic or non-aromatic? Lot of examples we are giving so that you can have an idea which is aromatic, which is non-aromatic, why it is so, why not other way. Pyrrole aromatic or non-aromatic?
Aromatic.
Lone pair of electrons and hydrogen comes into pi electron density moves away. So whenever you have a lone pair, that lone pair also can include which lone pair? Not all the lone pairs. that lone pair which is actually in the delocalization. Because if the lone pair is actually localized, then it is not involved, or it is not taken as a pi electrons. So we have 6 pi electrons, complete conjugation. So obviously it is going to be aromatic in nature. Very simple. Try to look at pyridine. Pyridine is aromatic or not? Can I include lone pair here now? 3 pi bonds. 3 pi bonds means 6 electrons. 2 more electrons are nitrogen because lone pair is there. Can I say 8 pi electrons?
No, sir.
No, because the lone pair of electrons and nitrogen, they were not actually involved in the delocalization. So they are localized because sp2 hybridized nitrogen, like nitrogen involving in the double bond, if it has lone pair, that will not be involved in resonance. 6 pi electron Huckel rule, complete conjugation, aromatic compound. I think this compound I have been given the structure also, cyclooctatetraene. It is also called as 8 aniline. 8 pi electrons are there, aniline structures, anilines. Aromatic or anti-aromatic or non-aromatic? 8 pi electrons are there.
And
Aromatic.
It should be non-aromatic in nature because of that structure. Whatever the CH bonds we have in this particular cyclooctatetraene, because of the repulsions between the hydrogens present, this structure exists in this fashion. Cyclooctatetraene exists in this fashion, so it is tub-shaped. So that means it is non-planar. The planarity is not present for cyclooctatetraene or 8 aniline. So absence of complete conjugation. Why? Whenever the planarity is not there, so this pi bond and this pi bond, they are not in resonance now. Although they are seeming to be in adjacent alternative double bonds, they are not in resonance because of loss of planarity. So that is why it is non-aromatic in nature. It is an exceptional case, you have to remember. Not like exceptional case, because reason is very clear, right? Because it lost the penalty. Why it is losing the penalty? Because of repulsions. Because of repulsions, the cyclooctatetraene exists in the top shape. Because of that shape, it is not planar. Since it is not planar, the complete conjugation is not possible. So it is not aromatic in nature, non-aromatic compound. Naphthalene, it is a benzonoid compound because benzene is generated. Benzene is present in this particular naphthalene, and aromatic because it has how many electrons? 5 pi bonds, so 10 pi electrons. 4n plus 2 is equals to 10. So 4n is equals to 8. So n is equals to 2. So 4n plus 2 pi electrons are there. So naphthalene has complete conjugation. 10 pi electron Huckel's rule satisfied. And that is why it is going to be aromatic, because it is also having planarity and all. So benzonoid structure, benzonoid aromatic compound. Why it is said to benzonoid? Because benzene is there in that particular structure. The repetition of benzene units are there. Similarly, naphthalene, if you talk of, you can also think of anthracene. Anthracene, if you take, it is also having benzonoid structure. How many pi bonds are there? 1, 2, 3, 4, 5, 6, 7, 7 pi bonds. 4n plus 2 is equals to 14. 4n is equals to 12. N is equals to 3. 4n plus 2 pi electrons satisfied. That is 14 pi electrons. And complete conjugation because of complete planarity. So it is going to be aromatic in nature. Is that clear, students? Everything so far?
Yes, sir.
Try to answer this question. Propone. Complete conjugation is there or not? Because this pi electron is can move into, this can move away, this can subsequently move into, this can subsequently move into. Complete conjugation is there. 6 pi electrons are satisfied. 6 pi electrons, because in the ring we have 3 pi bonds, so 6 pi electrons. So aromatic in nature, but not a aromatic. But not benzonoid. You try to answer these two questions. Which is more stable? Yes, these two structures, structure A and B. Which is more stable?
Mm.
Yes, Hima, A or B? Nandana says B. Why? Reasons are important, right?
Sir, more carbon, like the positive charge moves on more carbon, resonates on more carbon.
So more carbon means more stability. How we can say that?
The electron density is like shifted more,
Like that shifting is also there in A, no? Benzyl carbocation. The pi electron density can be in resonance with the CH2 plus. In A also we have the pi electron density resonance with CH2 plus. This resonance you can draw. 5 resonating structures you'll get. There also you'll get equal number of resonating structures. Okay, so B is more stable, that is true, but the reason is B is stabilized because of involvement of positive charge in the resonance with pi electron density, it gains aromatic nature. Okay, B is more stable than A. B is more stable than A. A also has aromatic nature, normal resonance is also there in A. B is more stable than A because it is aromatic due to involvement of positive charge, due to involvement of positive charge in resonance with the pi electron density. That means if I say A and B, among A and B, if B is more stable, then I can produce respective alkyl halides. I can use CH2Cl here. I can also give compound Cl connected here. Then I can do the reaction of these two alkyl halide in a polar protic solvent. In a polar protic solvent, SN1 reactions, they are going to be stabilized. If I do the reaction in a polar protic solvent for two compounds A and B, where I have connected chlorine groups here, then the compound compound B will be having a greater rate of reaction. The rate of reaction for compound B will be higher because if it undergoes SN1 reaction, the respective carbocation which is formed, that is stabilized and it is stabilized due to aromatic nature. Yes or no? So B will be having a greater rate for when compared to A based on this logic only, aromaticity only. Got it, everyone? So like that, you have to
Yes.
compare different cases. Try to say whether this compound is aromatic or not. Whenever we have been given with such compounds, we have to cleave the double bond carefully in such a way such that you will get aromatic for both the rings. You will have to check all the possibilities. The pi electron density I am giving to this particular carbon atom. So that means I'll write the structure in this fashion now. In this fashion. So this carbon has a positive charge, this carbon has a negative charge. These are the C double bond systems. Look at this ring separately. This negative charge in resonance with the pi electron density of that ring. This positive charge is in resonance with the pi electron density of this ring. So here we have 6 pi electrons, here we have 2 pi electrons. Both are aromatic, both are completely conjugation. Complete conjugation in both rings. Complete conjugation. So obviously, therefore, aromatic in nature. And you may ask a question, sir, why you are writing the pi electron density movement only in this direction? Why can't you write the other direction? Thereby generating negative charge here and positive charge here. In that case, both the rings are going to be aromatic, anti-aromatic. Is that stable? Anti-aromatic itself is unstable. So total both the rings are going to be aromatic means highly unstable. So that is why that movement will never happen. So this is the only accepted movement of pi electron density generating this structure, ultimately leading aromatic compound. Completely conjugation, Huckel's rule satisfied. So aromatic, and this is how you have to write the structures. The same structure we have written, right? 6 pi electron, 2 pi electron, complete conjugation, aromatic nature, and planarity is also satisfied. So then comes the next concept known as mesomeric effect or resonance effect. When an atom or group increases electron density in any conjugate system or withdraws electron density from any conjugate system through resonance, then this is said to be mesomeric effect or resonance effect. Like inductive effect we have seen, the plus I groups, electron donors, they increase the electron density. Minus I groups, they withdraw the electron density just due to electronegative difference. But mesomeric effect means the increasing of electron density or the withdrawal of electron density is happening through resonance, not through electronegative difference. If a group is there which is actually increasing the electron density, at obviously ortho and para positions only electron density can be increased or decreased. Mesomeric effect is applicable at ortho and para. So when a group or atom increases the electron density, it is said to be electron donating group. If a group is withdrawing the electron density, like decreasing the electron density, it is electron withdrawing group. So let us look at two types of groups now. Mesomeric effect is also categorized into plus M and minus M. Plus M means electron donation groups are there. Any atom or group which increases the electron density in the conjugate system is plus M. Any atom or group which withdraws the electron density from conjugate system, that is minus M. We can also use minus R and plus R respectively. Atom or group having lone pair or negative charge directly attached to conjugate system. Atom or group having polar pi bond or positive charge or vacant orbital directly attached to conjugate system. So let us understand plus M. So atom or group, like we have a phenyl group now. To the phenyl group we have OH connected, like phenol is there. The lone pair of electrons and oxygen comes into pi electron density moves away. So if you try to draw the resonating structures in phenol, you will get negative charges at what positions? Ortho and para. So if you try to draw the resonating structures in phenol, negative charge comes into pi electron density moving away. For all the 5 resonating structures, what you will be getting, students? In all the 5 resonating structures, you get the increase in negative charge or electron density at ortho and para positions. At ortho and para positions. And this OH is a electron donating group or electron releasing group?
Electron withdrawing.
Electron withdrawing or donating? Electron is donating, right? OH is actually releasing the electron density. It is electron donating group or electron releasing group. That means it will have plus M effect or minus M effect. Any group or atom which increases the electron density in the conjugate system, this is the conjugate system.
Plus
Electron
M.
density in conjugate system is increased by OH group. So OH group is what type of group? Plus M group. Also it has any inductive effect? Can I say minus I? Because oxygen is more electronegative when compared to carbon. It withdraws the electron density due to inductive effect. So OH group is plus M group as well as minus I group, and always mesomeric effect is dominating. Mesomeric is dominating when compared to inductive, except few examples. Like for halogens, inductive is dominant when compared to mesomeric. So this is how you can draw the resonating structures, where you have plus M group or plus R group. And if you try to write the resonating structures, in the second case, minus M or minus R, in that case, you should have a group G with a positive charge, like benzyl carbocation, or A double bond B, where A double bond B, A and B have electronegative difference. A and B have electronegative difference, stating B is more electronegative when compared to A. Like benzaldehyde you can take. Benzaldehyde, if you take, what happens? C double bond OH, like pi electron density moves away. So it is also minus M group, and you can also take CH2 plus. Benzyl carbocation, pi electron density moves away, so it is also minus M group. So minus M groups are electron withdrawing groups, and the electron withdrawing is happening by resonance, that is by minus M. And a lone pair of electrons present on the atom or negative charge, they will be electron donating groups, and they are plus M groups, that is electron donation is happening by resonance. Inductive effect is distance dependent, but mesomeric effect is distance independent. Distance is not going to be a factor in mesomeric effect. It is a permanent effect. Mesomeric effect on any atom or group operates only at ortho para positions in benzene ring. It has no effect at meta position. Although we have OH group placed at meta position with respect to some other main functional group, that OH can withdraw the electron density by inductive effect only, but it cannot donate the electron density. So at a meta position, whatever the groups are there, they exhibit only inductive effect. They will not exhibit mesomeric also, and they are not supposed to exhibit hyperconjugation also. You can write down that point. Even hyperconjugation is dominant or is operative at ortho and para positions, and not operative, and it has no effect. Like if we have a group set meta position, then you have to only think of inductive effect. It has no effect at a meta. Even hyperconjugation is operative at ortho para and no effect at meta position. Plus M group, that's what the resonating structures I have drawn, like OH group. Minus M group, C double bond OH. With respect to that, you can draw the respective resonating structures. So electron donating groups generates negative charge at ortho and para. Electron withdrawing groups, they will generate positive charge at ortho and para. So based on this, I can also comment on electrophilic substitution reactions of benzene and derivatives. If you have electron donating group, therefore electron donating group increases electron density at ortho and para. So therefore ortho para directors, therefore electrophile gets substituted ortho and para position. Therefore electrophile substitutes at ortho and para positions. Okay, at ortho and para positions only the substitution of the electrophile can happen whenever we have electron donating group. Why? Because they are increasing the electron density at ortho and para. If you have electron withdrawing group, but in electron withdrawing group decreases electron density at ortho and para, and thus electrophile substitutes at meta position. So electron withdrawing groups by resonance, they are meta directors. Electron donating groups by resonance, they are ortho para directors. Everyone got this or not?
Yes, sir.
Yes, sir.
Yes. Generally, mesomeric effect dominates over inductive effect, but in some cases, inductive effect dominates over mesomeric. What are those cases? Halogens, as I have told you, for halogens, and for C double bond O minus. For C double bond O minus, the plus M effect is great when compared to minus I. The plus I effect is great when compared to minus M. And some groups have both plus M and minus M effect. Example, if you take off N double bond O, it has a lone pair of electron. Because of the presence of lone pair of electron, it can be electron donating into ring. It has N double bond O pi electron density where oxygen is more electron negative, so it can also withdraw the ring. And we have S double bond OH. It also have electron donation tendency as well as electron withdrawing because it has lone pair as well as double bond O. Some groups has both the plus M and minus M effect. You may ask a question, sir, out of these two, whenever a group has both plus M and minus M, which is dominant? Plus M is dominant or minus M is dominant? That depends upon the reaction system as well. The group shows plus M and minus M both. You have to think of what reactants are there in that particular reaction mixture so that you can understand the total course flow of the reaction. Right, students? Compare plus M effect order. All of you do this question. We have to compare the plus M effect order. Based on electron negativity, you can see like CH2 minus, NH minus, O minus, NH2 minus. Simply negative charge can be donating easily, and negative charge present on carbon, nitrogen, oxygen. Oxygen is more electronegative. So when you try to compare these three, CH2 minus will be greater when compared to NH minus, then OH minus, then O minus. After this negative charge, you comes the lone pair. nitrogen. So CH2 minus NH minus O minus, because negative charge on more electronegative atom is stabilized. Less electronegative atom possessing negative charge is not so stable. NH2OHF, which will be having greater. Same logic apply. Lone pair of electrons on nitrogen, oxygen, fluorine. Nitrogen is less electronegative, so it can easily donate. So NH2 greater than OH greater than F. Right? So the same orders based on.
So,
Yes, please.
sir, in the first one, why NH2 is after O minus?
In the first one, this NH2 has lone
Yes.
pair of electrons or not? So negative charge donation is great. That's what I'm saying. Negative charge donation is great when compared to neutral. NH2 is actually donating the lone pair of electrons, whereas O minus is donating its negative charge. Okay, these are all negative charge donations.
Yes, sir. Okay.
Negative charge donation is great when compared to neutral lone pair donation. Okay.
Yes, understood.
OHOR, try to compare.
OR.
OR or OH, which is more electronegative?
OH.
I have explained earlier based on bond angle, right?
Sir, but there were more than one bulky groups, right?
OR2 plus, here it is
OR2.
ROPH system. Like here it is also a bulky system or not? We do not have any other hydrogens. It's not like alcohol. Yes or no? So here based on bond angle concept, we can say this oxygen is more electronegative when compared to this oxygen. Which oxygen is more electronegative? The oxygen OR is more electronegative when compared to the oxygen OH. So in that case, you can say, we can say the more electronegative oxygen cannot donate. So OH will be a better donor group. Okay. Oxygen in OR is more electronegative than oxygen in OH. If it is connected to, if the OH and OR are connected to hydrogen, then you cannot use the bond angle concept. Based on electron withdrawing group only, you have to say. Okay. Like we have H2 and alcohol. In that case, you cannot say bond angle and all. Based on electron withdrawing tendency, you have to comment. NH2OH, NHC double bond or OC double bond or. You try to take the fourth example as homework. Fine, students. We'll continue in the next class. Thank you all, everyone. Bye.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you.